Hey, Jake.
Hey.
I actually have a question for you. So, what did the dentist say to the golfer?
What did the dentist say to the golfer? I'm betting this has something to do with my foot in my mouth. Let's see. No, I don't know.
You got a hole-in-one.
I got a hole-in-one.
Yeah, one of these guys. All right.
Okay. Well played. Well played.
Well,
That's right.
all right. Well, thanks for coming by this afternoon. I am excited to announce that we brought presents for all you guys. If you check under your seat, we've got a piece of malware for you all. So go ahead, take out that piece of malware. And I want you to tell me, just based on this hash, is this file, is it good or bad? You know, let's do some malware analysis together here. Anyone can tell me? All right, so some people actually caught me here. This is the empty file. There's nothing going on with this hash. But how about this one here? You know, you're out doing an investigation. You found this file. Maybe some guy sent it to you. You know, what's going on? Do we need to worry about this? I don't know. What's our first step? My first step is usually throw it on Google, throw it on VirusTotal. Let's see if we find any results. I don't want to duplicate my analysis. I want to rely on the shoulders of giants, stand on the shoulders of giants. So let's throw it up on VirusTotal. But unfortunately, this thing hasn't yet been seen yet. So, yeah, right, definitely bad. This is probably malware maybe targeting my specific organization. Or it's Patch Tuesday. It's Microsoft binary. Nobody's uploaded it yet. And I haven't yet learned to check digital signatures. All right, so the next step, right, is open an IDA Pro. Who brought their license to kill? I mean, license for IDA Pro. Who's got that with them? All right, is this our next step? Although I love using IDA Pro, this is not my next step. It makes my eyes bleed. All right, I like using it. Not too much fun to use. All right, so my next step is usually maybe go and look at the PE features of this file. You know, look at its imports, make hypotheses about what the file may do, and maybe they'll drive my analysis. Right? I might wonder if I'm starting to think this is bad. Well, how do I find this file in my enterprise? You know, I got 100,000 systems to scan. Am I compromised? All right, next thing I might do, run strings on it. Just hoping to pull out some artifacts that might be sitting there in plain text. So we'll go ahead and do that. And this is what we get out, you know. Some things I'm happy about. I mean, I definitely see that DOS program up front there, the string there. It definitely tells me this is a PE file. I see some names of some sections right up front. But subsequently, it just kind of looks like junk to me. I don't really know how to interpret this. Now, what actually ends up tricking me is that this file is malicious. It's been obfuscated in some way, and yet I can't tell just based on the PE features or the strings of this fact. So it would be nice if we had some tool to tell us this, that sure enough, there are obfuscated strings in there and allow us to extract them. Except I jumped ahead a couple in my slides. So my next step, not knowing that information, is if I'm a reverse engineer, yeah, okay, it might be time for me to use IDA Pro, WinBag, OllyDebug. These are tools, very finicky, require a lot of advanced knowledge, but are very powerful, right? Takes a long time though, you know, and I may not have time during the incident response to focus all my attention on this one sample of malware. If I'm not a reverse engineer, I mean, I know we have some reverse engineers in the audience here, but is everyone here comfortable in IDA Pro? I don't see too many hands here. It's fine, right? So what do I have to do? I have to call up a reverse engineer. And Mauriz's here. He looks nice. He's a pain to work with. You know, he's not always on time. He listens to weird music. Sometimes he smells. You know, reverse engineers can be kind of weird people. We don't really want to deal with them. Sometimes they also cost a lot of money if we don't want to have one on staff, right? So we want to kind of avoid this. All right. So we have basically built a technique and a tool that allows you to very easily extract obfuscated strings from malware, and that's what we're here to talk to you about today. We already got a great introduction here about who the two of us are. As mentioned, I'm Willie Valentine. I joined Mandate about 6 years ago. I basically learned by doing, and so over time I've written a bunch of scripts and kind of shared them back, got a lot of good feedback, and interacted with many of you before, so it's exciting to be up here in front of you. These days I work on the Flare team, which is the FireEye Labs Advanced Reverse Engineering team, and this is basically a back-end service within FireEye that does most of the reverse engineering at FireEye. So we're looking at malware, exploits. We're located all around the United States. It's a fun place to work.
Yeah, and I'm Moritz, pretty new to the community. I started working at Mandiant or FireEye about a year ago. Did some incident response in the beginning and then got really sucked into this reverse engineering field. And that's what we've been focusing on now. And FLOSS is just a great example of the cool work we were able to do. And let's get right at it. I'm happy to provide some background first for malware. It's nothing new to you, but gives a good feedback of why string obfuscation is pretty common in malware and why we see it a lot, and why we figured we do something about it to make our life easier. So packing, I'm sure everyone here has seen a UPX packed file or similar packed executables. Everything that we look at in the on-disk executable is compressed, obfuscated, and the malware does uncompressing of that data in memory before executing. Can we go to the next slide?
To the right. And point it back there. I don't know.
It's not like a Wii remote, right? Oh! Yeah, so nothing new. There's a little unpacking stack that uncompresses the data and puts it back into memory. So when we look statically and with other tools at the on-disk executable, we won't get anything useful out of there. Strings are hidden. Yeah, it's just not very useful for our static analysis. On the other hand, it's pretty good for us as the good guys. When we look at this file, it's pretty obvious to tell that this is packed, and we can easily flag it as malicious because there might be a higher entropy of the file. The section headers might look off. It's just not like the general file we would expect that's benign. So pretty easy to tell this is evil. So instead, malware authors then hide their most valuable information only, which is often done in strings that get passed to Windows API calls, for example. Their names of C2 server addresses, file names created, files dropped, host-based, network-based indicators all over the place are encoded in strings. So those get obfuscated in the malware, and before using it in the code, decoded. So again, all we see when we run strings on this malware is a bunch of garbage. And this, when I look at these, some of these strings actually look like obfuscated strings, but there's no way to tell for us what obfuscation was used. Could be simple XOR of the bytes, could be RC4 encryption. And this technique is commonly used. It's used in commodity malware. I've seen it in Zeus, banking Trojans. I've seen it in some of the samples I looked at last week, which were related or attributed to APT 28, 29. They use it. So it goes from commodity stuff up to very targeted attacks. And when I look at this then, as a reverse engineer in IDA Pro, the yellow highlighted function here is actually a decoding routine. And the gray data there is an obfuscated string that gets passed to that function. And right before the malware needs that string or uses it, it decodes it. And there's no way for us to tell just by running strings in static analysis what we get here. So very annoying. Hence, there's some common techniques reverse engineers use to get this data back. First one being you need your reverse engineer and a debugger, for example, and it's basically just doing like memory forensics. You execute the malware, set a specific breakpoint, dump all the memory, and extract the strings out of that process memory. So it's very easy to do. Unfortunately, it doesn't work very often because strings might get deobfuscated after using them. It's easy to do, but doesn't work very often. Second technique then you could do, once you've put in some time, reverse engineered some of the code, identify the decoding routine, you again use the debugger to force the malware down specific code paths that you want it to take to obfuscate the strings for you. So you use the code of the malware. That's pretty cool. You make the malware work for you. And yeah, that's an easy way for you to do it. But imagine doing that 50 times for that one string decoding routine that is in there. It's a very tedious process. Takes a lot of time. Third approach you could take is you could re-implement the code you've identified in that decoding routines in your own code, scripting, Python code, C, whatever you prefer. This is an error-prone process, also very tedious. It might be good to apply this flexibly to all the data that you then also have to extract. So again, it takes a lot of time. Whole message of this is at least I would say for this, if there's a fairly sophisticated string decoding routine, you spend 2 to 3 hours reversing and getting those strings back, which you much rather could focus on figuring out what does the malware do, what interesting capabilities does it have, and the forensic analysts breathing down my neck will be also happy that I wouldn't spend much time on this. So that's why we came up with the FLOSS tool, the FireEye obfuscated string solver. And
yeah, just to emphasize what he said, when I first started reverse engineering, like I loved decoding strings. I felt like I was doing a lot. I would write these automated things to like extract whatnot. That was fun for like the first 2 weeks. And then I realized I had to do this every single week, multiple times per week. And each session was like 2 or 3 hours of doing this. Times across the whole year, 52 weeks a year. We have 30 people on our team. You can imagine how much time we're wasting doing the same thing over and over again. And there's just so many ways you can encode and decode strings that we might be able to build up a database of some existing decoders, but there's, the attacker only has to change one bit or one little tweak. It's an asymmetric warfare here. The attacker has such an easier time generating these binaries than we have reverse engineering them. So that's kind of our motivation here. So FLOSS, what is this guy? This is our FireEye obfuscated string solver. It's the solution to, well, just one of your problems, but hopefully a big one, right? Right off the bat, how do we use this thing? We use it just like strings.exe. It just gives us more data, okay? This is a key point here. We're going to use FLOSS to be strings and more. Strings plus plus, all right? We invoke it. FLOSS, file name. It gives us the data that we want. It's that easy. There's nothing more to it, all right? It's very user-friendly. How many of you guys have been to Black Hat or RSA or these great technical conferences, and you see a really interesting presentation, and you go home and you try it. You try to set up like Elasticsearch and Kibana and all these different things. And it takes like 2 weeks, and you still don't get it figured out. And you're kind of like, these guys are smart, but I can't live up to what they're doing, right? We recognize this. Although FLOSS is implemented, pure Python, easy to hack on, we give you a single standalone executable file that you can use, like strings.exe. You can download it today off GitHub. So it's easy to get started as we're talking here on stage with this tool. You already know how to use it. It's all open source on GitHub. It's free for everyone to use. We want to share this technique with you, all right? What is it? How does it work? Basically, we took Moritz, we scanned in his brain, and we turned it into Python.
Because you don't want to deal with me in person, right?
And we're sharing it with you, all right? We took the Flare team's expertise, their expertise in doing things like reconstructing control flow graphs, emulating code, extracting functions, disassembly, doing all this crazy stuff, and we make it easy for you to use, okay? So let me tell you a little bit about how it's using these techniques and these processes to make your job easier, all right? This is the algorithm right here, 6 steps, all right? Let's walk through it point by point. First thing we do, we got this PE file, right? We analyze it. We say, it's made up of functions, made up of code. What functions do we have here? You know, how are these functions related with one another? This is similar to when you open up an IDA Pro, a new binary, and you see it like do all these crazy things. If you don't know what you're doing with IDA Pro, you look over your friend's shoulder and you're like, he really knows what he's doing, right? We do a bunch of upfront analysis to have a good sense for what the binary might be doing. We then use heuristics to inspect each function to say whether or not we think this function could be an encoding or decoding routine, okay? That sounds kind of hard. How do we identify RC4 and base64 and XOR all together? Here's the insight. Oh. All right. We have a set of heuristics that inspect for each function. The heuristic says, I think this is an encoding routine. I don't think this is an encoding routine. You know, how do we encode this? I want to give you an example, all right? Here's a quick screenshot from IDA Pro. As a reverse engineer, what I see here, basic blocks, some assembly code, zooming in specifically right in the middle, I see this arithmetic instruction, this XOR instruction, that's manipulating a single byte of data. Right in the middle here, we see XOR AL with 7. We're doing a single byte XOR on some data. We then have some other arithmetic instructions Don't need to go into their details. Whenever I see this, I immediately think encoding, decoding, encryption, compression, okay? This is easy for me to program. I can say, just look for these set of instructions, the couple parameters that they may have, and do some reasoning about that. The next thing I identify, all right, is that this basic block is in a tight loop. At the bottom of this basic block, which is a kind of a discrete unit of code within a binary, I see a conditional jump. One branch, it's kind of red at the bottom there, allows the CPU to continue executing the next set of instructions. But the other branch of this conditional is back to the start of the same basic block. Okay, so these instructions get repeated over and over and over again. In my experience as a reverse engineer, this indicates to me that we're probably looping over a buffer, going byte by byte, applying those arithmetic instructions to each byte. Again, this is easy for me to do programmatically. I can say, give me all the basic blocks. Find all the ones that loop to themselves. Boom, I have a great detection routine for finding base64, RC4, single byte, multi-byte XOR routines, all the things that we commonly see in malware, easily captured by this, okay? Once I've identified the things that I think might be encoding or decoding routines, my next challenge is to figure out what data might be decoded. And so I continue to analyze the binary. I do some emulation. I basically virtualize some of the code, see how it behaves, to see what data is being passed into our decoding routines, okay? When I see data being passed in, I can take note of what data this is. And here's the trick. We can use a virtual CPU implemented in pure Python. We use this library called vivisect to emulate the decoding routine as the malware author implemented it, instruction by instruction, loop by loop, to operate on this data that we think is the ciphertext. And if we emulate this code correctly, we'll end up with a plain text. Now, one thing to note here is that this is purely a static technique. Although we're kind of virtualizing code, we're not doing it directly on the CPU. It's all pure Python. So unless you have some vulnerability in your Python interpreter, in which case you have a big problem, you don't have to worry about this taking over your system. FLOSS is a tool you can run on your analysis system because it's totally static, all right? You don't need a big sandbox or a bare metal system to run it, okay? This is pretty awesome. Finally, once we've emulated the decoding routine and we've seen how the CPU and memory states have changed, we can just do a diff in memory. What did our memory look like beforehand? What does it look like after? Any bytes that are different are places that we might have written the decoded plain text. And so we scan through that for strings. That's it. Was that pretty intuitive? Is that pretty simple? I hope so. It is. And it was surprising to me when it actually worked so well.
Yes, so we get all these cool decoded strings, and we really thought about it and had this idea that we could take this to the next level, as Willie already said, strings plus plus. So FLOSS is also able to extract all the strings that you get with the strings tool. So you get all ASCII and UTF strings using FLOSS. And a third category, which is also commonly seen in malware to obfuscate strings, stack strings, which are strings dynamically created at runtime, intermixed with instructions in the binary, so the regular strings algorithm doesn't get those strings. So you get 3 types of strings with the FLOSS tool, and really hope that you can use it and replace the strings tool in your analyst workflow, because you get all the strings that you would get anyway, in addition to decoded strings and stack strings. Also, we want to mention here, while there might be string decoding in a malware, it's not guaranteed that FLOSS always works. We won't get it right all the time. It's a hard problem, but it takes like 5 seconds for you to run FLOSS, which you want to see in a demo in a short time here. So there's really you don't lose anything by running FLOSS, but you can win a lot, as we're going to see.
Yeah, as we set up the video here, can we go ahead and play the first demo? What we found internally is our automated systems for analyzing malware, what our incident responders submit to the system. They've submitted like 45,000 samples since we started developing this tool. About 30% of those actually have obfuscated strings somewhere in them, and that we've been able to extract. All right, so we're not guaranteeing that every sample that you throw at Floss, you're actually going to get some results, but actually a good number of them, once you have a suspicion about this file, there's a good chance you'll actually extract useful information using Floss. So let's do that demo.
Floss demos always work.
What
Normally.
joke you had?
Let's rather wait for the video.
Oh, all right. You don't want to share your jokes. All right. We had a whole list of dentist jokes, but you guys gave us such bad feedback on the first one. We're not going to do that again.
Okay, so here we go. No need for bad jokes. So just gonna show the strings output of this executable here real quick. So we create the ASCII and UTF strings, and just gonna look at this file real quick, just to see a comparison that the strings we get later on with Floss actually are different. So we see our DOS header, section headers in there. Then text section, probably just a bunch of code. There's a high chance that the code actually looks like some kind of strings. Here we see those little 4-character type of strings. We're going to see those later again. Take a mental note here. Scrolling through, nothing really useful. There's some formatted strings. Start of our import table. So there's, yeah, nothing really useful.
Yeah. My suspicion at this point is it's probably malicious. I saw some weird strings formatted in there,
Yeah.
but I don't really know what the indicators are. So I want to extract these indicators really quickly so I can get back to my investigation.
So now we just run Floss invocation, super easy. Floss, malware, and then pipe it to whatever you want. Takes like, on average, I would say 10 seconds per sample to do the identification of decoding routines and emulation of those. And here we see, by default, it outputs all the strings, all 3 string types that I talked about. Static strings at the top, gives you a little header. Here we see those are the same strings we saw with the strings output earlier. Import table. Same kind of strings here. Then we get to our UTF 16 strings. The bottom, nothing useful or indicators to us. And then we get to the good stuff. So those are actually Floss decoded strings by decoding routines. So there's commands in there, file path. We can see there's some registry keys that we can go look for now. Another import, so this malware might be doing some process injection kind of thing. And then we also see stack strings. And those were actually constructed out of those little 4-byte characters that we saw. That's one approach the malware can take. And here we can see it's probably targeting Mozilla Firefox profiles and doing some extracting the proxy configuration from the Mozilla Firefox setup.
We've got about 5 minutes, so maybe we'll just keep going.
5 minutes? Okay, yeah. So can we do the second video? Or
Let's move along to slides. We have a couple times for time for extra
okay.
questions.
So yeah.
Okay, do the second demo. It's a good demo.
What do we do?
We'll go right through it. All right, so here we are working through a second malware sample, just demonstrating that it wasn't dumb luck when we ran our first malware sample through Floss there.
And this time we're just running Floss because we don't need to run strings anymore, basically.
Yeah. We've run Floss against
that tool.
Something like 250,000 samples right now. Basically every sample that comes in to FireEye as an EXE. We're extracting obfuscated strings. We're turning around right into the intelligence life cycle, turning these into indicators and figuring out what's happening at our client environments. And so I think the big thing to take away here is, one, this tool is already out there. It's free for you to use, to contribute to. We have a lot of people already contributing back to us. It's a standalone binary that you can be running with us right now in the same amount of time that we're running it. You can be doing it in your system, single standalone binary. It's like, why wouldn't you run this in the place of strings? That's our thought process behind it. So I hope we've convinced you of this. If not, ask us some hard questions now. Try to show a crack in our fortress here, and we'll convince you that I think Floss is a really neat tool. So
Yeah.
what
Well,
can
we
we
look
do
at
for you
some
guys?
of
Any
the
questions?
decoded strings here.
No? Okay.
Over here.
Waiting for the mic.
So hey, so aside from like just spitting out the strings that are decoded, is there a possibility to show like which function those strings were decoded from? So say like a single byte XOR.
Absolutely. So this tool is useful both as a reverse engineer. I would use kind of an expert mode here. If you're familiar with reverse engineering, that piece of information is useful to you. But we also wanted this tool to be very digestible by a wide audience. You know how to use strings. You don't know about function offsets within a PE file. We're going to give you output that you expect to now you can use on an investigation. And so by default, we don't get those function offsets. But I think if you pass the flag -x for expert mode, it'll give you all the functions identified. It'll group the strings by which function actually did the decoding. It'll show you where in the stack delta the stack strings were found. You can mark up your Radare or IDA Pro databases with these strings. There's a lot you can already do with this tool. Yeah, you got it. Up front here, if you ask it to me, I'll repeat it to the audience.
Let's do here.
Oh, I'm sorry. I'll cut you off. He can have the mic coming.
Wait for the microphone then.
Have you made any effort to either categorize or catalog any of the encoding and decoding routines you've been seeing?
I thought about that doing that first, but then as we already mentioned, there's so many things you could do, and with this emulation process we figured out, I think it's much more. Yeah,
Sure.
Yeah, it's much like
And one thing that's actually kind of neat about the way we approach this is using these heuristics, we actually have exactly 0 signatures for known routines like RC4 or base64. Like the base64 alphabet is nowhere in our binary. We don't depend on specific implementations. We're just able to guess which function is most interesting and kind of reason about it from there. All right, let's come back this way.
If the strings that are in the binary contain things like Chinese characters and whatnot, does it render those properly?
We would have a hard time differentiating that from binary data. I think that strings.exe also probably has that same issue. And so without more outside context to configure the tool in the right way, we would have a hard time extracting that information. Good question, though. Thanks.
I think that's about all the time we've got for questions. Guys, I really appreciate you coming out and presenting here. Awesome tool, great contribution to the community.
Thank you.
Thank you.
Thank you.
Thank you, sir.